A two-arm sprinkler is constructed as shown below. The total mass flow rate of water, density of 1,000 kilograms per cubic meter, is 1 kilogram per second, and it is divided equally between the two arms. At the end of one arm, a 12 millimeter diameter nozzle is oriented perpendicular to the arm and is in the same horizontal plane as the arm. The other arm has a 1 millimeter wide slot that also emits water in the horizontal plane. Find the rotation rate of the sprinkler in revolutions per minute, assuming that the pivot is frictionless. So we're also given a sketch of this system here. So a two-arm sprinkler. So we're looking at a plan view of this sprinkler over here. So this is the axis of rotation right here, and this thing is going to turn in this direction. So here's the nozzle exit, so that's 12 millimeter exit shooting out horizontally. And the strange thing about this sprinkler is the other arm has a slot cut in it. So water comes out uniformly along that slot. So we see the velocity of the water is uniform along that slot. At least the magnitude of the velocity coming out there is the same everywhere along the slot according to this sketch. This section AA shows us a cross section of that arm. So it's enlarged a lot over here, and there's the 1 millimeter slot that's cut in it, and the water comes spraying out that slot. And this also shows us that the slot starts 2 centimeters from the pivot and ends 15 centimeters from the pivot, and the location of this nozzle is over here at 15 centimeters from the pivot. So the given information is essentially this diagram. We don't really need to add anything to it. I think everything is on that diagram. We may add a few things to it as we go forward here. Let's recap what we're asked to find. And we're asked to find the angular speed in revolutions per minute eventually. So we need our list of assumptions. And we'll fill that out as we go along. Our analysis will begin here. So as with all of these types of problems, this is an angular momentum problem because it's a rotating system. So we want to start by identifying a control volume. The control volume that we're going to choose is going to cut through that exit and close both arms of the sprinkler. There's another exit, and like that. And that control volume that I've drawn there is going to rotate with this sprinkler arm. We also want a coordinate system on here. And again, remember the coordinate system cannot rotate with the sprinkler arm. It has to remain fixed. So I'm going to put a coordinate system that has its origin at the pivot. I'll call that X. And then Y is in this direction. So Z is pointing straight out at us. So the rotation here is around the Z axis. So we've established an inertial coordinate system, stationary with respect to the ground, and a control volume that is rotating. So our control volume is moving relative to our coordinate system. So we will have to be careful about that when we look at the velocities in our momentum equation. So going back to the momentum equation, we want to start with the full form of angular momentum. So we begin by putting that down. So the first thing in that equation is the torque produced by the body forces. So we have R cross G dV. And then the torque produced by pressure forces. So that is our R cross N times P dA. And then any torque produced by viscous forces, R cross FV. And then any reaction torque due to solid objects cut by our control surface. So that's the complete left side. We have an unsteady term. So the rate of change of all of the angular momentum in the control volume plus the rate at which angular momentum crosses the control surface. So that's our surface integral, rho R cross V times VR dot N dA. So we begin to take a look at what assumptions or simplifications we can make to this equation. So first of all, the body force term. Well, this is where we can look ahead and realize that we're actually only going to be interested in the K component of this because we're looking for rotation around the K axis. So even though this arm, the weight of this arm is going to produce a moment around the Y axis in one direction, and the weight of this arm is going to produce a moment around the Y axis in the other direction, they're not going to produce any moment around the K axis. So we can ignore this body force just because of the direction that it's in. So I'm going to just put up here, ignore body force. Next thing is our pressure force. So we go back and we look at everywhere on our control surface, and everywhere on this control surface is at atmospheric pressure. Remember, this is a free jet, and that's a free jet to atmosphere, so the pressure all along that control surface is atmospheric. The only place where the pressure isn't atmospheric is where our control surface cuts through this inlet pipe. So down below this pivot point there must be a supply pipe bringing the water into this thing, and the pressure in that supply pipe would be greater than atmospheric, but it does not produce any moment because it's coming in right at the origin. So the distance between the inlet and the origin of our coordinate system is 0. So what happens is this thing is 0. The R is 0. So either the pressure is atmospheric or the R is 0 everywhere. So that is gone. So we can say up here that pressure does not produce moment. Next thing are viscous forces. So again, we can take a look at our diagram. Here we have fluid just crossing the surface perpendicular. Same thing here, and in fact the same thing at the entry point where the fluid comes in at the pivot. So there's no shearing action at any of those inlets or exits. So we can say no shear forces. Last thing we have in our equation is the reaction torque. So remember, our control surface does cut through a solid object here where the pivot is. So there has to cut through a solid object because the base of this sprinkler, which isn't shown here, must be connected to it and must be cut by our control surface. But because we were told to assume the pivot is frictionless, there's no way that a moment can be produced around the z-axis there. So we can also say that this torque is 0. So we'll put in here frictionless pivot. So that's the left-hand side. Right-hand side, this is a steady problem. No reason to believe any of these properties are changing with time. So we'll just say here steady state. And so the last term we have here is just our flow of angular momentum across the control surface. So that's the only term left. So we have two exits. We'll label this number 1, and this one is number 2. And of course there is an inlet there, but that inlet is not going to contribute because R at the inlet is 0, because it's coming in right at the axis of rotation. So what we have left of this, 0 on the left-hand side. On the right-hand side, we split this up into two parts because we have two exits. The first one is a uniform exit. So we're going to assume uniform flow at 1 here. So uniform flow at 1. So this, whatever the velocity is coming out of there, it's the same all the way across that 12mm nozzle. So this becomes m dot 1 times R1 cross V1. So that's our first exit. The second exit, we have to be much more careful. Take a look at the second exit. Although the velocity is the same everywhere along here, everything inside that integral is not the same. And the reason for that is the position vector is also inside that integral. So the position vector has its root at the origin and its tip at any element of dA along here. And that is a variable. Also, the velocity of this fluid relative to our coordinate system is changing as we go along there. Velocity relative to the arm itself isn't, but the velocity relative to the coordinate system is. So that exit, this exit number 2, we have to treat as a non-uniform exit. So we have to keep the integral, set it up, and solve it. So the one thing we can take out of this is the density. So we'll do that right away. But then we're integrating over area 2 of r cross v times vr dot n dA. And that's all area 2. So what we need to do now is take a look at what all these r and v vectors are, so we can substitute them back in here, set up this integration, and get to this answer. So we'll begin just left to right here. What is r1 equal to in our coordinate system? Well, 1 is the exit over here. So r1 is just a vector with its root at the origin and its tip here. So notice when we do that, we're ignoring the little bit of a displacement in the y direction here. It's really only the distance from this vector back to this axis, or from the line of action of this vector back to this axis. So this is just going to be 15 centimeters in the minus I direction, because it's over here to the left. So that's 15 centimeters in the minus I direction. So I'm just going to call that minus R1I. So this capital R1 will substitute in 15 centimeters later on. Now, what is the velocity at 1? So that's the velocity of the fluid crossing the control surface at point 1, but in this frame of reference, in a stationary frame of reference. So what that's going to be is the velocity at the exit of 1. So I'll talk about that more in a moment, but this is the velocity of the water relative to the nozzle exit itself. And we can figure that out from the flow rate and the size of the nozzle exit. Okay, but that's relative to the nozzle itself. But we need to get this relative to the ground, so we have to subtract from that R1 omega, and all of that will be in the j direction. So go back and look at our diagram and see if this makes sense. So notice if this arm wasn't moving, if it wasn't rotating, then the velocity here would just be the velocity of the exit, and it would be in the j direction. But because this arm is moving in that direction, the velocity here is reduced. So the velocity relative to the ground is slower. And it's going to be slower by an amount equal to r times omega. So I've reduced that velocity by an amount r omega to get it relative to the ground. So when we take a look at these two together, we see that r cross v at exit 1 equals minus r1 v exit 1 minus r1 omega, and that all is in the k direction now because of the cross product. So that's our exit 1. We have everything we need for this. The mass flow rate we know because it told us what the flow rate to these arms was. 1 kilogram per second divided by 2 for the 2 arms. So that mass flow rate is half a kilogram per second. So we know everything that we need here. We will figure out this v exit at 1 later. So now we need to turn our attention to this other exit. So exit 2 we need to treat as a non-uniform exit, and we've already talked about why that is. Because the R and the V both are dependent on position, so we need to talk about that now. So first of all, R2, so that's a vector pointing to any element of area on that exit. So we'll notice the root is there at the origin, and the tip is at any spot along this exit. So that's going to be just the x coordinate. Okay, so R2 is equal to x in the I direction. Remember, we need direction on there as well. Now V2, the velocity of the fluid as it crosses our control surface at that exit 2 is going to be VE2, so that plays basically the same role as this. That's the velocity of the fluid relative to the nozzle itself, or relative to the exit at 2, but then we have to minus x omega. So notice that x is a variable. So the further we get away from the axis of rotation, the larger this effect is going to be. And that is in the minus j direction. So go back up and look at this. So this fluid is coming out in the minus j direction. The speed relative to our control surface was at VE2, but we have to subtract off the speed of the arm, which is r omega, and the r is varying. It's going from a low value of 2 centimeters here up to 15 centimeters there. So that's why this velocity is a variable, because this x is changing. Now, the rest of the integral here, so we've talked about the r, we've talked about the v. Vr dot n. Remember, this r means the velocity relative to the control surface, and the dot n means the component of that velocity perpendicular to the control surface. Well, we go back and we look at our diagram here. That is actually a constant, because the velocity relative to the control surface as we move along here doesn't change. This is a uniform velocity profile, at least relative to the arm itself. So the Vr dot n portion of this is actually constant, and it's just equal to this V exit 2. So we'll add that on here. So Vr dot n at exit 2 is just equal to VE2. And remember, there's a dot product here, so the result of that is just this scalar velocity, no direction. So we can also take this cross product up here. We need R2 cross V2. So R cross V at exit 2 is equal to minus x, so that's a variable moment arm. VE2 is a constant, minus x omega. And that's all in the k direction. So now we're ready to assemble, or to put all of this stuff we've been discussing back into our momentum equation. So we'll do that right here. So we have 0 on the left-hand side, minus m dot 1 r1 v exit 1 minus r1 omega k hat. So that's the uniform exit from the nozzle on the left side. And then the exit 2, we have a density. We have VE2 that we can factor out. We have a constant k that we can factor out. So this is the Vr dot n. It's constant, so I've brought it out. And we have our surface integral left. We'll do the limits in a moment. An x applied to VE2 minus x omega, and dx dz is our element of area. So go back up and look at that. So this area here is dx in this direction, and dz in and out of the page. So the limits of integration on that in the x direction are going to be from 2 centimeters out to 15 centimeters. And in the z direction will be from 0 up to 1 millimeter. So that's just integrating across this slot here. So we'll put those limits of integration on here. So we're going to go from 0 to L in the Z direction. So that L is just our 1 millimeter slot. And then I'm going to call this XA to XB. So those are two specific X locations. So A is right here, and B is right there. So we're integrating from those two values of X. So XA is 2 centimeters, XB is 15 centimeters. But I'll leave them as symbols now and just substitute numbers in later. So we have everything we need now to complete this integration. So we'll repeat this. So this is all unchanged. What I am going to do, though, is extract out the k component. The other way to look at this is we have this equation. We can just cancel the k vector off because it occurs in both of these terms. The other thing I'm going to do here is multiply this whole equation by -1 just to get rid of that minus sign and this minus sign. Clean it up a little bit. So m dot 1 r1 v exit 1 minus r1 omega plus, now because I multiplied through by -1, we have density v exit 2. Performing this z integral, there's nothing in here that depends on z. So the integral from 0 to L of dz is just L. And then we have this integration. So we have VE2 x squared over 2 minus omega x cubed over 3 and that's evaluated from XA to XB. So 0 equals m dot 1 R1 V exit 1 minus R1 omega plus rho V exit 2 L, and substituting in our limits of integration, we have V exit 2 over 2 here, XB squared minus XA squared minus omega over 3 XB cubed minus XA cubed. And we know everything that we need in order to solve this equation. So we have direct numbers to put in for everything except for these exit velocities, VE1 and VE2. We'll need to calculate numbers for those. So we'll do that. So V exit 1 is going to be the mass flow rate at 1 divided by the density and the area at 1. So we'll do that. So the mass flow rate will be 0.5 kilograms per second. Remember, there was 1 kilogram per second, and we were told that half of it goes to each nozzle, divided by the density, which we were given to be 1,000 kilograms per meter cubed. And the area, it's a 12 millimeter diameter nozzle, so we take our 12 millimeters squared and multiply by pi by 4, and that'll give us the area in meters squared. And all that works out to an exit velocity of 4.421 meters per second for exit 1. And then we have to do the same thing for exit 2. So mass flow rate at 2 divided by rho times the area at 2. Same mass flow rate because it's shared equally. 1/2 a kilogram per second. Same density. The area we need to be careful about, though, because this is a long slot, not a circle like this one was. And that long slot is 0.13 meters long and 1 millimeter in height. So those give an area of meters squared. And this gives a velocity of 3.846 meters per second. So now we have all of the numbers we need to substitute into this equation and solve for omega. So I'll put all of those in. 0 on the left-hand side still. Mass flow rate at 1, 1/2 a kilogram per second. 0.15 meters for the position of 1, R1. And then we have our relative velocity, 4.421 meters per second, that we just calculated up here, minus R, 0.15 meters, times omega. So that's what we're trying to solve for here. Plus the density, 1,000 kilograms per meter cubed, times this velocity, 3.846 meters per second. So that's our V exit 2 that we solve for here. 0.001 meters. That's our L, or the height of the slot. And then we have 3.846 divided by 2 meters per second. So I'll just show where we're at here. So this is this V exit divided by 2. So we're just filling in numbers for the rest of this. So XB squared, 0.15 squared, minus XA, 0.02 squared. Everything in meters there. So the units of that are meters squared. Minus omega over 3. And those same two x values, but now cubed. So 0.15 cubed minus 0.02 cubed, and those are both in meters cubed. So you'll notice that the only unknown in this equation is omega. It occurs in a couple of places, so we need to gather things together here. But omega occurs there and there, but it is the only unknown in this equation. So We can just simplify all of this stuff down. Get 0.075 here, 4.421 minus 0.15 omega, plus 3.846 if we multiply all of that stuff out. And then inside of here, this we can solve. That is 0.042498 minus that we can calculate out is 0.0011223, and there's another omega there. So we've just done a bunch of these calculations, and now we can actually solve for that omega, and that works out to 31.80, and have to remember this is going to come out in radians per second. So we can convert that to revolutions per minute. So we have 31.80 radians per second. So we need to remember there is that one revolution is equal to 2 pi radians. Okay, so those radians cancel, and that there's 60 seconds in a minute. So these seconds cancel. So we end up with revolutions per minute. If we take this 31.8, divide by 2 pi, and multiply by 60. So that omega finally comes out to 304 revolutions per minute.